Chapter 2 is chemistry. We're going to break this chapter down into two parts so that you don't have an overwhelmingly long video PowerPoint. Our learning objectives for this chapter include the following. What is the difference between an element and an atom? How do you read the periodic table? What is a molecule? What is a compound? What are the four macromolecules? What is a pH scale, and how do you define an acid or a base? What are the three types of molecular bonds? What are the important properties of water? And give examples of each property in action. What type of carbohydrates can we not digest? Describe the three possible outcomes to carbohydrates once they are consumed. What is the difference between a monosaccharide and a polysaccharide? List the three types of lipids. What is the function of each? List the functions of a protein. What is an enzyme? What is the composition of DNA and RNA? How are they different? Know the molecular progressive of information, from DNA to RNA to protein. As we continue through Chapter 2, please keep in mind Colossians 1:15 through 17. He is the image of the invisible God, the firstborn over all creation. For by him all things were created, things in heaven and on earth, visible and invisible, whether thrones or powers or rulers or authorities, all things were created by him and for him. He is before all things, and in him all things hold together. God made the big and the small. Our universe is ordered, and it is because of this order that we can study it with the scientific method. It's a good thing that God created our universe as being ordered. Imagine a universe where laws were constantly changing. How would we study it? Everything around us, living or not, is made up of atoms, the smallest unit into which material can be divided without losing its essential properties. An element is made of atoms. Atoms are composed of a nucleus and electrons. A nucleus contains protons and neutrons. An element is a substance that cannot be broken down chemically into any other substance. An atom is a bit of matter that cannot be subdivided any further without losing its essential properties. It is from the Greek indivisible. Let's look at the basic structure of an atom. The nucleus is the center of an atom. Remember, we said that the basic structure of an atom was composed of a nucleus and electrons. Electrons are particles that have a negative electric charge. The nucleus contains protons, which are particles that have a positive electric charge, and neutrons, particles that have no electric charge. If you have a problem remembering which particles have which charge, look at proton. You will see the first part of that word is pro, for a positive electric charge. Neutrons is very similar to neutral, having no electric charge. Let's look at the key to the elements. These keys make up the periodic table of elements. Each element is represented by an atomic number, which is the number of protons found in the atom's nucleus. You will also see an element symbol, an abbreviation of the element's name. You'll see the element's name as well as the atomic mass, which is the combined mass of the atom's protons and neutrons. To find the number of neutrons in an element, you must use both the atomic mass and the atomic number. Because the atomic mass in this carbon element is 12, we must subtract the number of protons from it, which in the atomic number we find to be 6. So 12 minus 6 is 6, which represents the element's neutron. Here is an example of the periodic table. You will find one exactly the same in the back of your book, with one exception. The one in your book is color-coded. Out of 118 elements, only 25 are in your body. So what are we made of? This diagram shows the top 10 elements found in your body. In this course, we're going to be focusing on the big 4. 96% of your body is composed of these 4 elements: oxygen, carbon, hydrogen, and nitrogen. An atom's electrons determine how and whether the atom will bond with other atoms. Atoms must bind together to form molecules. If atoms do not bind, then we do not exist. The number of protons identifies an element. What determines whether an atom binds with another atom? The answer is electrons. Let's look at the electron shell. Electrons move around the nucleus in designated areas called electron shells. An atom can have as many as 7 electron shells in total. These electron shells may not contain the same amount of electrons. For example, the first electron shell has a capacity of only 2 electrons. The second electron shell has a capacity of 8 electrons. The chemical characteristics of an atom depends upon the number of electrons in its outermost shell. These vacancies, as you see in this diagram, allow for this atom to bond with other atoms. When we have or do not have vacancies in the outermost electron shell, we can determine the atom's stability. An atom becomes stable when their outermost shell is filled to capacity. Stable atoms tend not to react or combine with other atoms. Let's look at the following example. This hydrogen atom is an unstable atom. It only has 1 electron and an electron shell that has capacity of 2 electrons. Therefore, there is a vacancy, and that vacancy will allow this atom to react or combine with other atoms. This helium atom is a stable atom. You'll see that it has 2 electrons in its outermost shell that has a capacity of 2 electrons. Therefore, there are no vacancies. Let's look at a more complex atom with 2 electron shells. Remember that we are looking at the outermost electron shell because the first electron shell is always filled to capacity. This nitrogen atom has 3 vacancies. Therefore, it has the potential to react or combine with 3 other atoms. This neon atom is filled to capacity in its outermost shell. Therefore, it is a stable atom and will tend not to react or combine with any other atom. Ions are charged atoms. An atom that loses 1 or more electrons becomes positively charged, while an atom that acquires electrons becomes negatively charged. Remember, an electron is a negatively charged particle. That charge is going to follow the particle when it is transferred. This transfer of electrons is driven by the fact that atoms with full outer electron shells are more stable. Atoms always look to become more stable. It is a preferential state of being. So let's look at the following example. Here we have a sodium ion that has donated an electron to a chloride ion so that both of them can achieve a stable state in having their outer electron shell completely filled. When the sodium ion gives up an electron, it now has 11 protons, 11 neutrons, and 10 electrons. Typically in an unaltered atom, we have the same number of electrons as protons. So when it gave up an electron, it now has one less electron than it has protons. Remember that protons are positively charged and electrons are negatively charged. So when we have an ion that has one more proton than electron, we see that that ion has a positive net charge. Now let's look at the chloride ion, which is receiving the donated electron from the sodium ion. Remember that we typically have the exact same number of protons as electrons in our original atoms. This atom, however, receives an electron, making it a chloride ion. We now have 17 protons and 18 electrons. Because we have one more electron than a proton, this ion demonstrates a negative net charge. Let's look at the following question. What characteristics of an atom gives it its chemical properties? A, the number of protons. B, the number of neutrons. C, the number of electrons. Or D, the number of electrons in its outer orbital. The correct answer is D, the number of electrons in its outermost orbital. It is the vacancies in the outer orbital shell that determine whether or not an atom will bind with other atoms. A sodium ion is a positively charged +1. How many electrons did it originally have in its outer orbital as a sodium ion? Please use the diagram provided. Is the answer A, 1, B, 2, C, 3, D, 7, or E, 6? Remember that we're looking at the positively charged ion. The correct answer is A. The sodium ion that is positively charged has more protons than neutrons. So we're looking at the sodium ion, which donated the sole electron from its outer orbital. A chloride ion is negatively charged, -1. How many electrons did it originally have in its outer orbital as a chlorine atom? A, 1, B, 2, C, 3, D, 7, or E, 6? The correct answer is D, 7. A negatively charged ion has one more electron than protons. So remember, we're looking at the chloride ion. It originally had 7 electrons in its outer orbital shell, and now it has 8, filling that outer orbital. Potassium chloride is found using ionic bonding. Potassium ions have a net positive charge, and chloride ions have a net negative charge. How many electrons were in the outer orbital of the potassium and chloride atoms? Is it A, 7 and 7, B, 1 and 6, C, 7 and 6, or D, 1 and 7? The correct answer is D, 1 and 7. The 1 electron in the outer orbital of potassium is donated to the chloride with 7 electrons in the outer orbital. The resulting is that now the chloride atom has 8 filling its outer orbital shell, and the potassium ion is now down to its last filled orbital shell. Atoms can be bound together in 3 different ways. Covalent bonds, which atoms share electrons, are the strongest. In ionic bonds, the next strongest, one atom transfers its electrons to another, and the 2 oppositely charged ions are attracted to each other, forming a compound. Hydrogen bonds, the weakest of the 3 types, involve the attraction between a hydrogen atom and another polar atom or molecule. Remember, there are 3 different types of bonds: covalent, ionic, and hydrogen. Covalent bonds are strong bonds formed when 2 atoms share electrons. Let's look at the following example of hydrogen atoms. Hydrogen atoms are most stable when their outer electron shell is filled to capacity. They can achieve this by sharing electrons in a covalent bond. The nuclei come closer together, and the 2 electrons begin to circle around both of them in a figure-8 pattern. The new H2 molecule is very stable. A double bond is a type of covalent bond. Let's look at this example given in the diagram. Each oxygen atom shares 2 electrons, and this is called a double bond. There are several different ways of representing molecular structure. We can use the Lewis model, the ball and stick model, and the space filling model. We'll go over these models particularly in our lab. Ionic bonds are formed when one atom transfers one or more of its electrons completely to another. This goes back to the sodium ion and chloride ion example. One atom transfers one or more electrons completely to another. The result is 2 oppositely charged ions. The 2 oppositely charged ions attract each other, forming a compound. The sodium ion and the chloride ion form NaCl, which is actually your table salt. Hydrogen bonds are important in bonding multi-atom molecules together. They are formed between a hydrogen atom in one molecule and an atom, often oxygen or nitrogen, in another molecule. In water, the hydrogen nucleus with only a single positively charged proton does not attract the negatively charged electron as much as it does the larger nucleus of the oxygen atom, which has 8 positively charged protons. As a consequence, all of the electrons spend more time near the oxygen. This makes that side of the molecule slightly positive and the hydrogen side slightly negative, just like a magnet, which has a slightly positive side and a slightly negative side. Hydrogen bonds are formed between the slightly positively charged hydrogen atoms of one water molecule and the slightly negatively charged atom of another. So let's review this one more time. The 3 types of bonds are covalent bonds, a strong bond formed when atoms share electrons in order to become more stable in forming a molecule. Ionic bonds, an attraction between 2 oppositely charged ions forming a compound. and hydrogen bonds, an attraction between slightly positively charged hydrogen atom of one molecule and the slightly negatively charged atom of another. Covalent bonds are the strongest of these three bonds, while hydrogen bonds are the weakest. Let's look at the following question. Calcium chloride salt, when put into water, is separated into calcium and chloride ions. Oxygen, on the other hand, is still present in the water as O2. How can this phenomenon be explained? A. Calcium and chloride are more strongly bonded together than the two oxygen atoms. B. Calcium and chloride are more strongly bonded together than the two oxygen atoms as a covalent bond. Calcium and chloride are less strongly bonded together, covalent, than two oxygen atoms, ionic. Or D. Calcium and chloride are more strongly bonded together, ionic, than two oxygen atoms, covalent. The correct answer is D. Calcium chloride are more strongly bonded together, ionic, than two oxygen atoms, covalent. If you were going to build a large macromolecule or polymer, it needs to be strong. What type of chemical bond would you think would work best for building macromolecules? A. Covalent, B. Ionic, or C. Hydrogen. Which of these is the strongest bond? The answer is A. Covalent. A molecule shape gives it unique characteristics, such as how the molecule tastes or smells, or its likelihood of bonding with another molecule. It all depends on the shape in which atoms are linked together and on the electrons exposed in their outermost shell. Different atom composition and how the atoms are connected yields different functions. This pertains to all molecules. Structure influences taste, insect mating behavior, and protein interaction. How a molecule tastes and how a molecule smells depends on its shape. Salt tastes different than sugar because different receptors on the tongue recognizes molecules of different tastes. A male gypsy moth can detect and track a female as far as 2 miles away if it encounters a molecule of her sexual pheromone. Hydrogen bonds make water cohesive. Hydrogen bonds are formed between the slightly positively charged hydrogen atoms of one water molecule and the slightly negatively charged atoms of another. Remember, it works like a magnet, and it is the weakest of the bonds. Because of water cohesion, water has a high surface tension. It allows animals, such as this lizard and this water strider, to, quote, walk on water. The V-shaped water molecules are held together by hydrogen bonds. These bonds are just strong enough to give the water a surface tension with net-like properties. The hydrogen bonds between water molecules gives water several of its most important characteristics, including cohesiveness, a reduced density as a solid, the ability to resist temperature changes, and broad effectiveness as a solvent. Be sure that you remember these 4 interactions of water molecules that give these 4 properties of water: cohesion, large heat capacity, low density as a solid, and a good solvent. Cohesive is not just water tension. Because of the cohesive properties of water, trees, such as the giant sequoia, are able to transport water molecules from the soil to their leaves, 300 feet above. How does this work? Well, as each water molecule evaporates, it pulls up additional water through the tree because of its stickiness of the hydrogen bonds that link the water molecules together. Water has a large heat capacity. It takes a large amount of energy to heat up water. Heat from the sun disrupts some of the hydrogen bonds from the water molecules. New hydrogen bonds are formed almost as quickly as they are disrupted. Because the heat energy from the sun is used to break up and reform hydrogen bonds, the water temperature doesn't increase by much. Molecules that make up the sand, on the other hand, don't have many hydrogen bonds, so the heat of the sun just increases the temperature. 60% of your body is water. This helps you to maintain a relatively constant body temperature. Thirdly, water is low density as a solid. Ice is less dense than water. This again is due to hydrogen bonds. Hydrogen bonding arranges water molecules into a crystalline lattice, keeping them slightly further apart and therefore less dense. In liquid, water molecules move about more freely, allowing them to be closer to one another. The fourth property of water is a good solvent. In a solvent, the gas or liquid in which a substance is dissolved. Let's look at the example of dissolving table salt in water. When placed in water, ionic compounds such as NaCl are broken down into separate Na positive and chloride negative ions. Positively charged sodium ions are attracted to the negatively charged side of the water molecule, while negatively charged chloride ions are attracted to the positively charged side. Salt water does not freeze well because of the lattices of the hydrogen bonds that cannot form in salt water. Let's look at the following question. Fish live in water. What property of water is important for the survival of fish during winter? Is it A, cohesion, B, heat capacity, C, ice float, or D, water is a good solvent? The correct answer is C, ice float. Because ice is less dense than the liquid water, the lakes and oceans do not freeze from bottom to top. If they did, where would the fish go? Ice also insulates the water so that it does not get as cold. Why does water display the unique properties we have just discussed? A, because of the covalent bonds between the oxygen and hydrogen. B, because of its ability to hydrogen bond. C, because of its ability to make and break ionic bonds. Or D, because the electrons are shared equally between the oxygen and hydrogen atoms. The correct answer is B. It is all because of water having hydrogen bonds. The pH of a fluid is a measure of how acidic or basic the solution is, and depends on the concentration of dissolved hydrogen ions present. Acids such as vinegar can donate protons to other chemical bases, including baking soda, bind with free protons. Again, the pH scale is a measurement of the acidity of a solution. Acids have a greater amount of hydrogen positive ions. Bases have a greater amount of hydroxide, OH negative, ions. pH is a measure of acidity based on the amount of hydrogen-positive ions in a solution. So, for example, stomach acid has a pH between 1 and 3. Acids are shown as on the pH scale as being from 0 to 6. Bases are shown on the pH scale to be from 8 to 14. 7 is neutral, which is about where water is. Let's look at the chart here. Acids are fluids that have greater proportion of hydrogen-positive ions to OH-negative ions. Hydrogen-positive ions are very reactive. Strong acids are very corrosive to metals. For example, have you ever seen how metal reacts to Coke? Coke, or soda, has an acidity level on the pH scale of 3. And if left to it, they will dissolve and break down metal. Acids break down food in your digestive tract, and acids are generally sour in taste. Bases are fluids that have a greater proportion of OH-negative ions to hydrogen-positive ions. OH-negative ions bind with hydrogen-positive ions, neutralizing acids. Strong bases are